welcome you are to lecture number 2 on Advanced Engineering Mathematics course. So today we discuss part A, that is ordinary differential equation. My name is Dr. Bilal Khan. Now first we start first order ODEs. So in this is the first chapter of your book and we will discuss the first order ordinary differential equation. So ODE means ordinary differential equations by deriving them from a physical or other problems, normally when we do the mathematical modeling. So whenever we did a mathematical modeling of a dynamic system, we come up with a differential equation. Now what do you mean by dynamics of a system? So dynamics means that if you have a system which contains some energy storing elements, or in digital system where you have some memory elements included, so when we try to model those physical system, we introduce differential equations. So the simplest ODE to be discussed are first order, because it involves only the first derivative of unknown function and no higher derivative. So first order ODE means that you have only single derivative in the equation. So these unknown functions will usually be denoted by y of x or y of t when the independent variable denoted t. Uh, so what we learned till now is that when we say that first order ordinary differential equation, so this means that the equation contains only the first derivative of unknown function. Now what is modeling actually? So if we go to, we have a physical system. So from this physical system we come up with a mathematical model. So when we do the mathematical modeling, after mathematical modeling we come up with the mathematical solution of those mathematical equations. And when we get the solution, then important thing is physical interpretation of those solutions, which is very important, so that we can interpret our mathematical model uh, according the real phenomena. Now these are some applications of ordinary differential equation. For example, falling stone from a tower. So when we look at the falling stone and there's a height, and we know that the rate of change of its speed is actually equal to the acceleration is due to the gravity, so it is equal to g, so equal to constant. So this is because it will fall with a constant speed. So this is an example of modeling. Similarly, we have velocity for a paratrooper. So when we model it, it becomes also a first order differential equation. Similarly, we have water level tank, and so these are some few examples where we can apply this mathematical model. So these are physical phenomena, and these equation actually represent those phenomena. And normally, because this system has some dynamics, so that's why we come up with a differential equation. Now first our differential equation, which we already discussed, that it has only single derivative. Now there are two forms that can represent it of this first order differential equation. One form is known as implicit form, where your derivative is within the equation. You cannot separate from the equation. So that form is known as implicit form. When you can separate the derivative and non-derivative terms separately, you can write it, then in that case it is known as explicit form. So there are two forms of representation. One is implicit and other is explicit. So the graph or the curve of h of x is called solution curve. So let's do a quick example here. So verification of the solution. For example, if we say that the solution of a differential equation is y is equal to c by x, where c is arbitrary constant. So if it is solution of x y dot equal to minus y, so for all x is not equal to 0, So when we apply this and we put y is equal to c of x in this differential equation and take the derivative and put there. So when we do that, we get the same result. So this means that they satisfy the equation of the differential equation. So it means that we get x y hat equal to minus y. So this means that it will satisfy the equation of differential equation. So y is equal to c by x is actually solution of differential equation. Now, the solution we discussed in previous slide is known as general solution. Now we normally have a particular solution. How we get a particular solution? Particular solution means that we have to know the value of c. So how we get the particular solution? For that case, we use initial value problem. So a differential equation together with the initial condition is called initial value problem. So we have a differential equation here. Explicit equation is written that y dot equal to f xy and y of x of 0 is equal to y naught. So if we look at example how we do that, for example, we have initial value problem that is given that y dot equal to 3y and y of 0 is 5.7. So when we solve this equation, and as you know that we get the solution y of x equal to c exponential 3x. Now from here, to calculate the value of c, we use the initial condition. Initial condition says that when x is 0, then value of y is 5.7. So when we put 5.7 is equal to c exponential 3 into 0, from here c becomes 5.7. So hence we calculate the value of c when we put y of x is equal to 5.7 into exponential of 3x. So this is the solution of this initial value problem. Now we look at some more on modeling. So here, for example, the step one is that the transition from physical situation or physical system to its mathematical formulation. It's a mathematical model. Okay, so this is the first step when we do in modeling, that we have a physical system and we transform into a mathematical equation. Now the second step in the modeling is that the solution of a mathematical model, uh, we apply different techniques to find to solve those mathematical equations. Now when we get the solution, then we come out to step number 3, that is very important, the physical interpretation of the result. So we have to interpret the result physically so that we know that what this mean actually, because from when we solve a mathematical equation we get some numbers. So what these numbers means in terms of physical behavior or phenomena, this is very important. So third step is the most important step to relate your results to the physical phenomena. Now I give you a quick example here which involves the first order differential equation and is known as radioactivity, where you have exponential decay. Okay, so for example, if we are given an amount of radioactive substance, say 0.5 grams, and we have to find the amount present at any later time, so thus decaying in time. And from physical experiment we know that the substance that is decaying, radioactive substance, is actually proportional to the substance present. For example, if you have more substance present, so as it has more decay after some time. So decay depends upon how much substance available. So hence the mathematical model of this physical process in the initial value problem can be written as the rate of change of substance is proportional to the substance available. Okay, so when we say that y is the substance available, so if we take the rate of change, that is dy by dt equal is proportional to y, which is the substance. So to make the equality introduce, we say equal to minus kx. So because we know that it's decaying, so that's why it is minus k. Now we know that initially we have 0.5. So this is the way we can model a physical phenomena. So as you know that whenever you do modeling, Using first order differential equation, normally it has only single variable or single variation that depends upon the other phenomena. Okay, so radioactive decay, exponential increase, or population, these are models used normally first order differential equations. Now, after that, we will start geometric meaning, directional fields, and Euler's method. Now, I will stop here and I will continue in next lecture further. Thank you.